Students, and I'm really impressed with the students here. You consider yourselves very lucky to have this generation of really brilliant young people, insightful, innovative, and hungry to be part of UH. That's the first thing I want to say. The second thing I want to say is, my colleague, he's not going to bring me here and just like say all this stuff, and I'm going to say something about him. Tony, I guess some of his close friends would call him that, and colleague, is one of these individuals, a rare individual that just, he doesn't mince his words. And so I remember one time I was going through a rough time in Dartmouth, dealing with some colleagues and stuff, and he goes, you need to learn how to play in the sandbox with others. I don't remember that. He's like, man, I need you here to support me. You're not telling me to play in the sandbox with people. And I think that really captures, how great and how envious I am that he is your colleague and he's here. Because, as a hard time you've given me over the years, you have such integrity. And everything you say, you live. So thank you so much for having me here. And thank you all for having me here. And I hope that I don't put you asleep. But what I want to do tonight is to sort of, get you a little bit hip to some new discoveries, some new connections that have been made, some of which is summarized in my book, The Jazz of Physics. I have a new book coming out soon called Cosmic Improvisations. And so let's get on with it. But the first thing I need to do is actually set things up here. So please just bear with me for a quick second. All right, here we go. Okay, I said this, a lot of this talk is based on my book, The Jazz of Physics. Let's begin. So a good portion of my talk surrounds these two questions. The first question is, what drives scientific creativity and innovation? And in fact, we can generalize that to just the question of what drives innovation and creativity. But when I talk to a bunch of scientists, I like to put this question out because oftentimes those of us who grew up in the scientific community, we're not necessarily looking to jazz music as the driving force between that. And then, of course, a second question we're going to address in this lecture is in which hidden ways is physics and astronomy connected to music and jazz improvisation? Again, that's an absurd question to ask, right? So we're going to address these questions. And to give you a little bit of insight, it begins with this computer scientist, cognitive scientist, whose name is Douglas Hofstadter. Does anyone know who this person is? Okay, I see a young man put his hand up there. Who's Douglas Hofstadter? Speak loudly.
He wrote Gödel, Escher, and Bach.
That's right. Hofstadter wrote the book called Gödel, Escher, Bach. It's a gigantic tome, okay? And I still have this book. I only have it in my office to impress my friends. All right? But the basic point is that this guy is actually really smart, okay? And he's a cognitive scientist. He was a physicist and became a cognitive scientist. So Hofstadter basically so what I'm going to be doing today is making analogies. I'm taking jazz music, or music in general, and I'm taking physics, astrophysics, and cosmology, and I'm going to be making analogies between them. So, well, what's the purpose of making an analogy between things that have no connection to each other? Hofstadter said, analogy is the core of cognition. What makes human beings, what the core of cognition meaning, our ability, cognition is a mental action or process of acquiring knowledge and understanding through thought. We make analogies. We have, from the time we're babies, we take things that we are familiar with, which is a bottle that ends up in my mouth, and the bottle is round, and I see a chair, it's round, maybe they're the same thing. And then these comparisons that we make, and analogies we make between things we understand, and we have direct experience with, and things we don't understand, we use analogies to help us understand things we don't understand. So there's a lot of stuff going on in physics and in cosmology and about our universe, for example, and about what's in front of us that we don't understand. But there are things we understand well, we have direct experience with, and by making analogies, we can actually understand that it gives us insight or directions that we can go in to understand the unknown better. So today, I'm going to do a two-way analogy making. I'm going to use our direct experience as human beings with music. I walked in and I just played, actually I just made something up as I walked in. And I played a bunch of musical tones, and somehow you had direct experience of that. And what I'm going to do today is to show you how those sounds that you were hearing can give us deep insights into the inner working of our universe. And if that sounds crazy, I'm going to try to prove that to you today. So, this begins a little bit with a little story about what brings me here today. My parents immigrated from Trinidad and Tobago into the Bronx, New York when I was 8 years old. And I grew up in a musical family. My father was a cab driver, my mother was an emergency room nurse. And I was a very inquisitive young person. I was one of those weirdos that would as an 8-year-old kid, I remember I used to wave my hand in front of me and wonder what's space. I used to look out my room window and look at the stars and wonder what was out there. But a lot of young people do that. Young people in general are very inquisitive about the world. It's usually, adults that shut it off. Well, other young people, all right, it depends. But the point is that I grew up in an environment where there were no scientists around. I grew up in the Bronx, New York in the 80s. And so there was a lot of push for me to kind of become a musician. And I started piano lessons at a young age. But I knew I used to read Marvel comic books. And wanted to build the Iron Man suit. I was very inquisitive. But I didn't really see any role models, any scientists around that looked like me. So I kind of took to music. And unfortunately, a lot of the music that was being propagated at the time, and it was less so back then than it is now, was rap music. In fact, rap music came out of the Bronx during that time. And then what happened was, this happened. Does anyone recognize who this individual is? Okay, I see the guy with the long beard. Eminem called him the greatest MC of all time. This is Rakim. And he did an album in the 80s. And this album became the biggest splash in hip hop music. And he became the person that all the young people were sort of looking up to. And the thing was that he basically started rapping about science. And in fact, he belonged to a sect called the 5 Percenters, and they believed in something called supreme mathematics. And when they rap, they call it drop-in science. So I'm going to play a line from, hopefully this works. What's he going to do is pull up this YouTube video and play. I want you to listen to the lyrics at the beginning, okay? Give me some more volume here. That's good.
Check out my melody and out a cigar. I'm letting knowledge be more than my name's the R. A.K.I. am not like the rest of them, I'm not on the list. That's what I'm saying, out of minds like a scientist. My melody's in the code of every next episode. Have the mic off in the store, ready to explode. I keep the mic at Fahrenheit, frequencies are made with cola. The listener's system is kicking like solar.
Okay. So, what does this mean to a 14-year-old boy growing up in the Bronx? He's a role model. These days, when you have a big shot rap star talking about being a gangster and all this stuff, young people are listening to that. As a young person, I have this guy who's talking about making allusion to scientific, he's battling his other rapper by say that he can control the laws of nature, and he's making allusions to scientific concepts. This is huge. Okay, it was so huge, it made it okay for me to walk down the streets and tell my friends that I want to be a scientist. Right? So that's what Rakim represented. And for those of you who want to, I urge you to check out the guy is really a genius. He was also a jazz saxophonist before he became a rapper. So from a musical perspective, his cadence is like bebop music. So Einstein was a person that I became aware of by mistake. I got lost in the Museum of Natural History as a third grader. And instead of going to see the dinosaurs, I walked into some other room and I saw a picture of this weird-looking guy with crazy hair, drawing a bunch of equations. And I immediately felt connected to him because I think this guy's a weirdo. And he didn't fit him like me. He has weird hair, and he has these weird symbols, and I wanted to decipher the symbols. I had no idea what it meant, but I was curious. And then the other person is a guy named John Coltrane. Again, just to remind you, as a young person, I have this tension, this inner turmoil about wanting to become a scientist, not having any role models around, and this push to become a musician, where there are tons of role models around, and I'm trying to reconcile this throughout my life. And as I'm going through, I'm discovering these individuals, and these are some of the three people that stood out. The other one was John Coltrane. When I was in college, I discovered the album Giant Steps and The Love Supreme, and of course my favorite things, right? And but there's a lot about Coltrane that you don't know. So this is a hand-drawn diagram that Coltrane actually gave to Yusuf Lateef as a birthday present in 1961. And what happened was I discovered this diagram in the middle of my postdoc. I couldn't solve the problem. I was stuck in a particular physics problem for 6 months. And I was hanging out with a friend of mine in San Francisco who was a jazz musician, and I discovered this diagram. And then something weird happened, and I saw some patterns in that, and the physics problem I was working on, I was like, this is really weird. What's Coltrane onto? So why the Coltrane that you and I know in the sort of public sphere there's a hidden Coltrane. And what does this mean? And hopefully by the end of the talk, you'll understand a little bit about what this means and what this has to actually do with the universe. So I'm just going to rush through. So basically, in a nutshell, all throughout my college years, I'm living a double life. At nighttime, I'd go to jazz clubs and sit in with a jazz band. At daytime, I would just be a physicist, and those worlds didn't talk to each other. Here's a funny joke. I lived in London for a couple of years, and there was this woman I was very much in love with, and she was way too cool for me, right? It was like that, that usual story, right? So, and she knew me and said, well, what do you do? I said, I'm a jazz musician. I'm a jazz. Oh, that's cool. So we kept having lunch, and I'd bring my sax case in and sit down. And, I was a postdoc in physics at Imperial College, but she didn't know that. I'm kind of like telling the half-truth, right? So I'm not lying. So I'm sitting down, and then we're talking, and I'm like, wow, this is like my fourth date with this woman. It's going somewhere. And then I go to grab my sax, and it opens out, and out splurges a bunch of physics papers. So the papers go on, she grabs a paper, and she looks and she goes, what's this? It's the philosophy of music, whatever. She goes, so you're a physicist, The turning point, though, was this individual. How many people recognize who this person is? I'm talking about the short hair guy. Excellent. That's Brian. For those of you that don't know who Brian is, you know who these people are, and he is responsible for their careers. So he's one of the legendary producers, and he also is known for something called generative music and ambient music. He's behind, but did a lot of those stuff. Brian and I he became like a mentor of mine. Right? He lived in the neighborhood that I lived in London, and we remained friends. And he was the one that changed things for me.
Foxy music.
Thank you very much. So one day I had an open door policy in Brian's studio. On my way to work, I used to stop in his studio a couple of days a week, walk in, and he'd always be working on some kind of project. And one day something changed. I walked into his office, into his studio, and he was wearing a wizard's hat and a wizard's robe. Okay? So I'm like, okay. What are you on? And then he had these gigantic computer screens with these type of things. So I'm like, wait a minute, this guy's lost it. Like, is he playing some kind of prehistoric video game? I come back the next day, and he's still playing with this stuff. So then I approached him. I said, hey, Brian, can you explain what this is about? What are you on? What are you doing? He goes, well, I'm working with something called cellular automata. All right, I don't want to go into what that is, but basically, it was some, fairly advanced types of mathematics and computer science ideas that he knew very little about. But he was using that to come up with some new art. And 17 years later, it became pieces like this, called generative art, that was acquired by Apple Computer. So the point there, the lesson there for me was, if this artist could just, be a dilettante and just jump into, advanced mathematical ideas and use it without any shame in his art, well, I should be shameless too. I should just, find ways, combine my music world and my physics world. So he kind of inspired me to say, I don't care. That I don't care moment. And so Brian was the one that really inspired me to do that. Good, so that's part one of my talk. That's a kind of a little bit of a warm-up to kind of, capture a little bit. And now what we're going to do is part two, is I'm going to demonstrate to you that there are some deep connections between music, sound, and the happenings and some mysteries about our universe. Are you ready for this? Okay. Before I do that, I have to give everyone the same tools. And the tools I'm going to give you are some of the most important ideas in all of science. Normally when I give this talk actually, a similar talk to Google headquarters with all the engineers at Google in Mountain View. And I made this following statement. I said, this on this screen here is the most important idea in science. In fact, if you were to pick an idea that kind of like is used in all the different branches of science, this would be the idea. And it's called a Fourier transform. Now, any scientists in the room? Okay. All right. So close your ears, you're ready to know this stuff. This is for everyone else. So the idea is that I'm going to give you a common language, and so once you know this language and you know this tool, we'll be able to use it in the music domain and in the physics domain, in the cosmology domain. And it's going to be sort of like the glue. Are you ready for this? Okay, so here we go. The Fourier transform was discovered by a French mathematician. And the idea is as follows. Suppose that you're looking for an alien life form in outer space. And you get very complicated signals from outer space. Well, ET is not there to translate that for you, right? But, you know, if you were to speak to someone in Russian, and you don't know Russian, and you have a translator, what the translator does, it takes those Russian words and translates it into English, and they can understand it. So what we would like to do, if we get information for which there is no translator, we have to figure out a way around that. And the tool that we use in science, and particularly in physics, is this idea of waves. One thing we understand, so for example, one basic thing in computer science we know is zeros and ones. And with zeros and ones, we can make a computer do this stuff. So the basic alphabet of computers is zeros and ones. In physics, it's actually waves. What do I mean by that? So what we're looking at here are what we call very special waves, meaning that they're what we call periodic waves. They're waves that consistently repeat themselves in a very simple periodic pattern. And you can characterize them by two things. How rapidly they oscillate, okay? And how high the oscillation is. Surface, obviously, like the big ones. And so the idea here, the two pieces of information I want you to understand, is that if you take two simple periodic waves that's oscillating, that's undulating at the same rate, and you add them together and they overlap, we call that in phase, they will give you a wave that of the same oscillation but a higher height. Okay? Or if I take two periodic waves and they completely don't match, in this case, they're what we call out of phase. If you add them together, they cancel out. We understand that because we see stones dropping on the pond to create complicated waves. Or for those of us that like to get bombarded by waves in the ocean, we see that as well. Using this idea that waves can add up or waves can cancel, we can do the following thing. We can say, let's take more of them. We have periodic wave, a longer oscillation, fast one, and something in between. If I add them up using these two principles, I get a more complicated waves. It doesn't completely cancel, nor does it completely add. So now we go and say, let's take 10 of those things. Then all of a sudden, the important thing I want you to understand is to just get the feel for this, not or how do I add up 10 waves. That's if you take a course with me, right? We will learn how to add that up. That's the important thing, is to get the idea. And the idea I want you to get now is if I take a whole bunch of waves and add them up together, I get a complicated wave. So now, I say to you, you look at your telescope and you get a complicated wave signal from outer space and want to know if it's ET trying to talk to you. What do you do about it? Check out what's cool about this. The same way I can add waves together to get a complicated wave, the Fourier transform tells me I can do the reverse. Given a complicated wave, any complicated wave, I can decompose it into simple waves. I can do the inverse, the reverse of it. And we can use that because we understand the alphabet of waves to decipher complicated signals. So obviously this is using cryptography. Okay, it's one of the tools that's used. It's using signal processing. It's using MRI. It's using your cell phone. It's a very important tool. Now, of course, the hook here is that sound is a wave. Since I'm going to be making connections to physics and music. So you're going to be like, wow, this guy, so this is a very important tool, and I hope in 5 minutes I've given you enough. And of course, since I'm a physicist, I have to prove to you that what I'm saying is not BS. What we're looking at is a computer simulation of many of these simple waves added together, the blue ones, and you add them together, and you get a square wave. So people that do musical synthesis, this is how you make a square wave signal. Okay? Or you can take a square wave and decompose it. You can do the reverse. And these are the equations that do that for you. That's the only time you'll see an equation in my talk. But it's so beautiful I have to show it to you. But now, remember I told you about analogies? And the power of analogies is that it's a lens, okay? Or if you want to think about it, it's a window or an orientation to which something that at first appears to be complicated, if I find the right angle to look at it, it's simple. So I'm now going to prove to you that you already know what the Fourier transform is with my horn. So what we're looking at is how waves are represented in a wind instrument. In this case, it's some corny flute. So what I'm going to do now is to do the following thing. I'm going to take the simplest wave that can exist in an instrument. So I create an air wave. The saxophone is a cheat because you should actually straighten this out. And what will happen is that you create waves, air waves, that basically, so the lowest note on my saxophone will be the one up there, right? Because it's the one that's vibrating at the lowest frequency. Look at that. I'm getting all excited. Okay. So I'm going to play that note. I'm going to play the lowest note. Alright? Now, what happens if I clip the wave in half? Any guesses? I don't want any people that know the answer to give me an answer. I want someone to guess. Yeah. I see the young man raising his hand in the back. What's the answer? If I clip the wave in half, what would it sound like? So it would be the octave?
Well, exactly what I think.
Yeah. So I clip the wave in half, and I get the octave. How about if I clip the wave in thirds? Any guesses? All right. I'll play that for you. Ready? The perfect fit. It is harmonically the most important note in classical music. All right, how about, let's go beyond this. How about a fourth? I clip the wave in 1/4. You get the perfect fourth. My zero is song called 4. It's based on that movement. Close. So, notice something. What I showed you before about the Fourier transform and added waves is actually our musical scale. And that's what Pythagoras discovered, the 580 BC. We'll get back to that in a second. So you already understood, growing up singing Do a deer, a female deer, Ray, a drop of golden sun, me, a name. I call myself. 4, a long way to run. That's the 4. whatever it goes. I need to watch that movie again. But the point is that you already understood that. And I gave you another way of thinking about it. And by analogy, you can have a deeper understanding of something that you didn't understand. And we're going to take this a little bit further now. This is a picture of a guy named Johannes Kepler. Everybody knows the name? All right. So in a nutshell, from the time of the ancient Greeks and the ancient Egyptians, we were trying humanity, some human beings. I mean, some were, doing the battle of Gilgamesh and, wrestling with dragons in the ocean and things like that, for classic lovers. But some are trying to understand the motion of planets. They were trying to understand what creates motion, what is motion, all right? By looking at the night skies, a lot of these things were ascribed to demigods. And then at some point, people were saying, well, maybe we see patterns in the sky, so maybe there's something that's making this happen. And for 2,000 years of extremely bright people, and I like to tell my students the following thing. It's like you saying, it's going to take you, think of a problem we're trying to solve today scientifically, and it's going to take 2,000 years to find a solution. We live in a time where we've been very spoiled because in the last 100 years, we've had a golden era of major discoveries. But before that, you're talking about 2,000 years to try to understand a simple thing as what makes planets move. And so for 2,000 years, until this time, Johannes Kepler comes on the scene. And he spends 40 painstaking years. He had a very hard life, by the way. His mother was almost burnt as a witch, and he managed to get off that one. He lost a couple of kids. He apparently took only two showers in his life. He had a tough life. But Kepler was the first person that was the first astrophysicist. Kepler was, what do I mean by that? He was the first person in history that actually wrote equations for the motion of planets. That were correct. That not only explained phenomena, but also predicted phenomena. That's why we have a satellite called a Kepler satellite to actually find new planets using Kepler's laws. It's still relevant today. The question is, how did he come up with that? And I don't want to get into the entire history. There's a whole chapter in my book about this, going into the history of this. But in a nutshell, Kepler believed in Pythagoras' idea that the universe is playing a musical harmony called music of the spheres. And he said, well, let me try to see if that works here. And what you're looking at down there is his own handwriting. See, Saturn, Jupiter, Mars, Earth, Venus, Mercury, Sun. All right? And here is what's interesting. What Kepler does, first of all, he didn't know that the planets were going around the sun. But he said that if the universe is playing music, like Pythagoras suggested, there must be some divine being at the center of the sun enjoying the motion of the planets. So therefore the planets must go around the sun. So he aligns himself with Copernicus for the first time in thousands of years. And then he takes, so here's the sun, here is a planet going around the sun, say it's Earth, and as it's closest to the sun, he realizes that the planet is moving fastest as it goes around the sun, and here it moves slower. And what he does is exactly what I showed you with those vibrations, that if I took 1/3 and 1/2, so he finds the ratios of those velocities and writes down notes. Wow. And he generates the major and the minor modes of the musical scale from that. And it was through that analogy that led him to Kepler's 3 laws of motion, making him the first astrophysicist. Now it was much later on that Isaac Newton used Kepler's laws as a motivation to come up with his universal law of gravitation. And the story begins for the flourishing of what we now call our modern physics. He got to it by using a musical analogy. So in a lot of ways, what I'm talking about today is nothing new. So now I want to take you into today's time. Now, what do we know about our world today? Well, they're no longer only like, a bunch of planets going around our sun. Now we know that not only are there billions of galaxies, right, in our own billions of planets in our own galaxy. Remember, our galaxy is a collection of stars going around a common center like a frisbee, and we now, have evidence that every star, there's about 2 planets per stars, and there are about 500 billion stars per galaxy, like our own star, our own sun, which is a star. So you're talking about trillions of planets. But we now know, and I might get this number right, so it's wrong, so we're not getting it, but they're in the order of like, a billion Earth-like planets in our own galaxy. So we can't do the Kepler dance anymore. But the question is, can we do music still? Can we do a musical analogy to the universe today? And that's what we're going to do right now. What we're looking at here is what we call a large n-body simulation, supercomputer simulation of how the large-scale structure in the universe organizes itself. What do I mean by that? So imagine you look at this distance scale. This is about 7 billion light years across. Recall that 1 light year is about 10 trillion miles. That's 1 light year. So if I imagine I want to zoom into this area and see what's up, I zoom in and I get this little area here. I want to zoom in here. Now we're looking at about 35 million light years in distance, and every dot is a galaxy that contains billions of stars like our own sun. So I want you to now revisit your vision of empty space. You think that empty space is this vast randomness of emptiness. But when we take the bird's eye view of our universe, at least the parts that we can see, we see structure. And physicists and cosmologists, we want to understand that structure because we know, just like a biologist would know, our dean of sciences, a geneticist, knows that structure informs function. And that theme also applies in physics as well. When we see structure, it means that there's some hidden function that's making galaxies do what they do. And the question is, we'd like to understand, is where did the galaxies come from? Because our galaxy is our home. Our galaxy is what we call a stellar nursery. It's a region where stars are born. And stars, remember, is what's feeding plants light energy so they can do photosynthesis, so that we can breathe oxygen. So we like to understand this kind of physics. And we have another piece of thing, which is this picture. Now that picture I showed you is here and now, today. The picture we're looking at is from 13.8 billion years ago. It's light, so remember when you look at sunlight, the sun is about on the order of 90 million miles away from us. And it takes light a certain amount of time to travel to us. So the light we're looking at when we see the sun is a couple of minutes old. Because, right, it takes light, just like when you see thunder before you hear it. It takes a sound, so a little bit longer to get to us. Well, light actually has a finite speed. That's what Albert Einstein taught us. So we could look at light that's 13.8 billion years old. And what that light gives us is a fossil imprint of what the universe looked like 13.8 billion years ago. The same way, looking at a star 5 million years ago gives us an imprint of what the star looked like 5 million years ago. It's a bit weird, but that's just the nature of how our world works. So what we're looking at here is a picture of what our universe looked like 30.1 million years ago. And here's what's interesting about this picture. Let me just give you a quick summary as to what we know. Albert Einstein predicted that space, our universe, has been expanded. And one of the questions I always ask myself, who cares if the universe expanded? Like, do I care about the universe expanding? It's like I wake up in the morning, oh, the universe expanded a bit more. Okay. So that's actually an interesting question. That's a whole other lecture. Dr. Tillis, please invite me back and I can talk about what I call cosmic inflation and not, economic inflation. So the universe, which means the following. If the universe is inflated, think about blowing up a hot air balloon. If I take a balloon and it's filled with hot air and I compress the balloon, it gets hotter and more dense. Right? So when the universe was a universe that expanded, it means in the past it was more dense and hotter. Imagine the universe gets so hot, so amazingly hot, that all the atoms and all the matter boils into pure radiation energy. So there was a time in the universe's past, if you believe that the universe has been expanded, that the universe was filled with pure radiation and energy. And there was no matter around. It was a seething soup of energetic radiation. And this picture confirms that. So what you see in here, you see the blue and the hot and these colors, the red and the blue, they correspond to different temperatures. So the picture you should have is like the surface of the sun. You have undulating waves of thermal energy fluctuating. And it's very hot. It turns out, so you look at this, and the question that physicists we ask ourselves is how could this, what appears to be chaotic, featureless, energetic universe, as it expanded, become what we see it, what we know about our universe today? Which I'm having a hard time getting back to my, this. How does it become the gazillions of galaxies and stars and people and places that we know to be? What is the physics that made that happen? And so, remember I told you about analogies, right? What I mean by that is the following thing. Physicists were presented with this problem way back in the 50s. And when they looked at the equations that govern this behavior, it seemed intractable and very hard to solve. And then someone had the right intuition. A couple of people, some Russians and an American physicist named Jim Peebles at Princeton. And a paper was written in the 70s where an analogy to sound was made. So again, you look at this, it looks chaotic, and the question is, can there be an analogical perspective that makes things easier? And I've given you all the tools now that you need to understand this. So I'm not going to have to water anything down, because I talked about the Fourier transform, and now we're going to use that the first thing to take notice of, the red and the blue spots actually correspond to what we call pressure waves. A pressure wave is a sound wave, by the way. Air pressure undulating under high intense pressure, and low pressure is what's created the sound waves from the instrument. Good. Let's look at actually what happens when I actually blow a note into my saxophone, or a flute for this matter. Bear with me for 1 minute, because it'll be very much worth it. On the right-hand side here, as I go up, and if I go up from left to right, every point corresponds to one of those waves that I talked about. So when the number is low, you should picture a very long periodic wave. As the numbers increase, the wave becomes even more curved. And I move more it becomes even more rapid. So every point gives me an impression of how loud a given tone is played. So by example, if I look at the bottom there and I look at this axis up there, is how loud that tone is. If I were to kind of impressionistically play that for you, this will be a low note and it'll be very loud. And if I go there, it's kind of low when I go to a high note. And if I go to high notes, it gets a little bit higher. And it corresponds to all these different waves. This is a very important tool in science. We call it power spectrum, okay, or spectral analysis. But what it does, it gives us a signal for how many waves are produced. In this case, when I play a note, in this case a G note, on my flute, what I actually end up seeing or hearing is not one actually note, but many, a whole slew of different notes. But your ear actually hears the dominant note, the one that's loudest. What does your ear actually hear about the other notes? Anybody got a guess?
Could be the texture of the music.
You nailed it. If I have an oboe and a flute play exactly the same note, you will actually hear the loud one, which will be that note. But the woodness of the oboe is the other vibrations that the instrument is producing. And you hear that as a signature sound of the oboe. And the flute is made of metal. So the flute will vibrate in different ways. So your perception doesn't hear the note, but it hears all those other frequencies, all those other undulations as a signature. That's why your voice sounds different than somebody else's voice. You have a different makeup. So these other frequencies capture the uniqueness and in a lot of ways the material that the instrument is made up of. So there are two things I want you to take away. When an instrument plays a note, the note that's the highest and loudest is the one you actually hear as a note, but the other frequencies you don't directly hear. You just hear it as what makes a flute sound like a flute and a trumpet sound like a trumpet. Make sense? All right, great. That's very important. So these other vibrations reveal the material makeup of the instrument. Good. So remember I told you that we looked at this data of the early universe and we're trying to make sense of it. And we don't understand the correct physics that's allowing for this early universe and these undulations of energy to somehow become stars and galaxies that we now inhabit. Complete mystery. How do we go from that situation to the situation that we find ourselves in? What is the right way to think about this, especially when this thing looks completely chaotic? So let's use the analogy. Let's actually take these undulations that we see in the data, and they are representations of waves, and ask ourselves the following question. So here's the data, and what we can do is say, I want to look at large areas and large waves and compare how many of them are similar to each other. That's like asking how loud they are. How many of those big waves are in the picture? Right? And then I say, how many are the small waves? And what I do is plot. Just like I did for the instrument. Right? I'm doing exactly what I did for blowing into a flute. I said, I want to see how many waves of given sizes is coming out from the instrument. I'm doing the same game because I'm trying to make sense out of it and I'm using an analogy for sound. I do that and I plot. So that's how the data is actually being constructed. There's a $3 billion satellite and data mission that was used to do this. So, so it wasn't like we were like, playing games here, but we were. And this is what we get. So we go from that picture, the analogy is this is your flute, your instrument, to this picture. So this is what you get. And I want you to compare it to a more complicated thing, which is an instrument actually produces many frequencies as you go to higher frequencies here. Frequency meaning how rapidly a wave is oscillating. And what we see is actually, the early universe looks like a very simple instrument. What we see here is, forget these dots, I'll explain what that is in a second. Let's look at a curve. What we see is a frequency of vibrations in the early universe that's playing a note that is the loudest. That would be the tone you hear. And it turns out to be 220 hertz, which is the A note. Okay. And these other frequencies here is very similar to these other things I heard in my flute, these other frequencies, that somehow we know, if we were to take the analogy seriously, I ask you the following question: what should these other frequencies correspond to, if you believe the analogy? Because remember, the point is we're going to use something we know to learn something that we don't know about, this chaotic thing, right? What would the analogy tell us about what this might mean, these other frequencies? There's a picture of the universe, right? So let's go back to our analogy. What those other frequencies reveal was the material makeup. What made the oboe is made up of wood versus a flute made up of a certain type of metal or alloy. And depending on the details of those frequencies, it will give me information about how much aluminum or how much metal, iron, or cobalt is in that instrument, or is it made up of a different type of wood. So if we were to use the analogy and take it seriously, it would say, what would it say about our universe at that time? The structure and makeup of the universe. That's what it would say. Agreed? If we were to just blindly use the analogy. Good. What we see here is the data. These dots. This is 20-something years of data taken of 3 different satellites. And this curve here, this data have been taken since like 89 all the way up until 2005. It takes a lot of painstaking observation in outer space to look at this data and to pin it down very precisely with, we're talking about a millionth of a degree in fluctuation above the average temperature in the universe. Very precise measurements, very advanced technology. And this actually represents a theoretical curve of a prediction that was made by Einstein's theory of relativity, the expanding universe, done in the 60s. And what that theory says is that our universe, in its primordial state, before galaxies were formed, had hydrogen in it that became stars as these fluctuations actually collapsed to form stars. But the rate at which these collapses happen to form galaxies, you needed extra stuff like dark matter and dark energy, and that these curves, the relative peaks in these curves, will reveal the material makeup of our universe. So yes, our universe in its early stage was actually functioning like an instrument. So the analogy actually turns out to be kind of bang on, correct? Okay, so that's sort of like the meat of like my talk was kind of like walk you through a little bit of my journey and what led me to really continue, sort of looking at these analogies. But I want to kind of end on and take it to another level now, and it actually has to do with pushing the analogies further, and not necessarily, by the way, to unveil new truths or to appear to be clever, but just for the sheer fun of it. Just to play and to learn new things and make new connections, because after all, that's a big part of being a human being. Amen. Right? So I'm going to end with like Dr. Tillis. How am I doing with time? All right. I'm going to say something very, so Let's actually now go into the cell phone. I like to tell students that if you don't believe in the cell phone, if you don't believe in quantum mechanics, you shouldn't own one of these. This is a quantum mechanical device. So if you want to give me a cell phone, then you should, if you don't, then you should listen to this. Quantum mechanics is really weird. It's very strange. The architect of quantum, one of the main architects, Richard Feynman, said, I assure you, no one understands quantum mechanics. All right? So I have colleagues that write books about quantum mechanics and have no idea what I'm writing about. And let me tell you why it's weird, okay? I'm going to reveal how weird it is. So one of the things I do as a physicist is to try to understand things that I think I should understand better and more and more. So that means I try to find different ways of thinking about it to give me a deeper insight. And so I find that this analogy made with music is helpful. I'll give you an example. In the world of classical physics, of the very big, which is not quantum, we know very well that I'm not going to drop this because I have to pay for it. But if I drop this thing, it starts with some given position, and it's going to follow a very distinct trajectory, probably a straight line, from point to point. That's what objects of our everyday experience do. But in the quantum world, in the world of the very small, the world that makes up the world of large, it doesn't happen that way. What happens, and what we know to be true, is that actually when a particle goes from point A to point B, it actually traverses every possible path that's smooth and continuous from point A to point B at the same time. And that completely goes against every bit of intuition we have about me doing this. It's like me, I just split up into 5 pieces and, I tapped Antonio in his head, he doesn't know what happened. That would be great, The point is that, I can be a trickster if I was a quantum particle. Right? But we know this to be true because experiments have been done to confirm this picture. And so one of the things I try to do is to understand, to try to make better sense of this. So this is what we call a Feynman path integral, and it works, experiments have been done. We've made quantum devices based on this. The quantum computer idea is based on this idea. Let's actually think about jazz improvisation and what happens sometimes. So I had the fortune to speak to Sonny Rollins when I was writing my book. And he explained to me actually how he improvises. And he said, well, there are many ways you can think about improvising, but here's one way I like to think about it. This is actually a transcription of one of his solos. And notice that it begins on a given note, this is D, and ends on a G. And remember, D and G is related to each other harmonically. I want you to think of only the beginning note and the end note. And I want you to think about the initial position of a particle and the final position of a particle. And I want you to make an analogy and think of the initial note as the particle moving through space, and moving through time. So if I start off on a given note, and I end at another note, start off on a given note, and I end at a given note, I can imagine following many different paths that connect this note to that note. And what an improviser does, subconsciously or by some magic, is consider many different paths at the same time. So at a given time, some of your rounds might go down and go up. You connect that. Go up, do something else. And so that analogy basically tells me that maybe what's going on with the quantum particle is that it's not doing all this stuff, but it's basically just improvising its way from point A to point B. And you say, well, why is that interesting? Well, that's a whole other discussion about what we call quantum ontology, meaning trying to make sense of the awareness of quantum mechanics. But I'd much rather accept that electrons are improvising than playing dice. Albert Einstein has this famous saying, God does not play dice. And it was really an attack on this particular picture that it's all probabilistic and random. Okay? I like the idea that nature improvises. So that was interesting. connection to make there. And I kind of want to end now with, I said a little bit about how music and physics could actually inform, ideas in music could inform as analogies physics, at least the kind of physics I work on. I want to actually talk a little bit about innovation and what was going on with jazz music in the 40s, in particular bebop music. We're looking at a picture of Charlie Parker at Minton Playhouse. And I want us to go back to that time. During that time, a lot of musicians were playing swing music downtown in Manhattan. And that music was very, in the eyes of the musicians that were playing, it became kind of rote. Every night you got to, play, and it's very regimented. It's good stuff, it's swing music. But the musicians at that time wanted to not just perform, they wanted to make art. They wanted to innovate. So what they would do is after they did their gigs with Count Basie and Dorsey, they would go uptown to Harlem, 125th Street, to Minton's Playhouse, and then play music for each other. And they would experiment. And they would make mistakes. So instead of making a kick drop before a beat, they changed that to the ride, playing that before. Or there was a time when Max Roach made a mistake and his kick pedal dropped at the wrong time. And then someone said, this sounds pretty hip, let's keep that. They call that dropping bombs in bebop drumming. All right, so a lot of these mistakes came out as innovations in bebop jazz. And the case I want to make now is that if you look at what was going on in physics during the same period of time, with the revolution of quantum and the revolution of relativity, there were similar things going on. That when we look at innovation, right, it's not always due to logical reasoning. It comes from making mistakes, and it comes from embracing these mistakes, right? Right. So, I wanted to just speak to that very quickly. And in fact, one thing I think that actually physics today and science today could learn from jazz musicians and jazz, the culture, is coming from a guy named Albert Murray. So he was a visionary of jazz at Lincoln Center, and he was responsible for actually deliberately iconicizing jazz music as America's art form. And if you want to understand how huge that is, when I lived in Europe for those years, that's all that, at the top conservatories in Europe, they praise jazz music as something that they could never come up with. And, there's a long story about that, I won't get into it. And there was this idea that Murray came up with as to what is the fuel of jazz, one of the cultural fuels, and he called it antagonistic cooperation. And it's this idea that you can be the worst musician in the world, okay, and go to a jazz session, and they will let you sit in with them. When I was 16 years old in New York, I used to go and sit in with some of the top, Wynton Marsalis, these guys. They'll let me sit in with them. And I'll be the worst musician. There was an inclusivity embedded in culture, but it wasn't like they would give you an easy time either. They had high expectations of you. So there was an antagonistic cooperation. It's kind of okay to be criticized, but it's coming from a place of love. And that was a fuel of jazz. And what I call recombination. New innovations from infusing what appears to be different traits. This actually happens in genetics. And I kind of want to now end with culturing, because I started with culturing. What does this have to do with anything I said here? Because culturing was this type of musician that was not satisfied with the status quo. He clearly mastered his craft, but realized that tradition was about defining tradition. And tradition was also about defining tradition. So he studied the music of China, he studied Arabic music, he studied Indian music, African music, and he figured out ways to bring it together. He was very much also into all different types of, mysticism and, including, Christianity. Coltrane was all over the thing. But one of the things that he was very much into was Albert Einstein. And everything he gets his hands on about Einstein, he would study. And actually what we're looking at is Einstein. I have a question for you. What do you see in this diagram?
I think it's the circle of Fifth, right?
Okay, so that's what songs represent. But in terms of pictorially, what do you see? You see stars. You see lots of different, right? You see lots of different stars. In fact, you see what we call symmetry. A star is a five-sided object. So that means it's symmetric. That means if I rotate the star, right, 5 times, I get a star out of it. And that's exactly the root of Einstein's theory of relativity. Einstein's theory of relativity is a symmetry principle. I don't want to get into that for too long, but Coltrane understood what Einstein was really about, and that the underlying architecture of physical law is governed by symmetry. And Coltrane actually revealed to David Amaran, who was the first composer of the New York Philharmonic. They were friends. I had the fortune to meet David Amaran, who told me himself that Coltrane said, what Einstein did for physics, I want to do for music. And so I think Coltrane serves as a really good exemplar for this form of analogy making. And on that note, I'm going to end. I'm going to end with this very interesting picture. This is another symmetric diagram. And the first thing you see here is this represents a neutron, and this represents a proton. We're made up of neutrons and protons, right? All nuclear matter, hydrogen, helium, iron, it's all neutrons and protons and electrons, right? And these other things here are actually what a neutron and a proton can become. It represents higher order vibrations of the neutron and proton, and notice it forms a symmetric pattern. This was a model that used Einstein's idea of symmetry that helped us land the theory of what we call quantum chromodynamics, which is the underlying theory of the nuclear force. So again, we use Einstein's idea, and it helped Murray Gell-Mann get the Nobel Prize. And this picture basically summarizes, and I hope strikes a little bit of resonance of what John Coltrane was trying to do with his music. I covered a lot of ground today, but that's why I flew all the way out here. It was kind of like a bit more perplexed. And thank you for your time.
We do have time for questions. We have 2 mics here, and after, if you have a question, just please come to the mic. We have roughly about 15 minutes for questions and dialogue.
Good evening. I enjoyed talking. As a jazz improviser, are you familiar with the concept of a flow?
Yes.
Or you could say a pocket. Do you think there is an analogy for that in intellectual pursuits of physics, let's say?
Yeah, I mean, we have to be, so you asked a question about the concept of flow. Sometimes, it's called, it don't mean a thing if ain't got that swing. All right, so swing, what makes something, jagged versus something that is aesthetically pleasing in terms of music, in terms of rhythm. I have a colleague, Robert Roth, at NYU Steinhardt School, and there's a whole research field of the study of rhythm. So I don't really have much to add to that degree of expertise. All I can do is just, be a dilettante and pretend like I know what I'm talking about. But one of the things that we would love to understand in physics, what we call continuity, it's an assumption that we make about things, that things are usually continuous and smooth. But we know that there are examples in nature where we get discontinuities, for example. When the weather pattern all of a sudden flips on us, and all of a sudden we can't predict the weather. Or, when you have a tsunami that happens, there are discontinuities. And so there are examples where we don't have flow. right? So the answer is I don't know about flow. It's a good question though. And I think it's I think that's something that you should think about yourself and pursue on your own. I mean, go to graduate school and get a doctorate on it. I'll be able to take care of it. Yes.
Have you met Rakim yourself, and how old is that gentleman today?
Oh, thank you. Yes, so I had the fortune to meet Rakim. National Geographic had an event that with Rakim and a guy named Damian Marley. They did a project together called Distant Relatives. Damian Marley is Bob Marley's one of his sons, and they did an album together. And I had the fortune to attend that event. And then, of course, Rakim was there, and that was like I think 5 years ago. And so Rakim had his concert, and then I waited and went backstage, and I said, I just want to thank you, for and he goes, God's always say, well, he was 5% of Cyprus as it's called. But that was a very important moment. So I did get a chance to meet him and thank him.
Did you draw an analogy to help us understand dark matter better?
No. You were asking a really hard question. Which I like.
You brought up earlier about Brian Eno, and some people imagine him as kind of the father of electronic music and the trance that you brought into it, and the production that he did with Bono and as far as with bands throughout the years. But knowing that you were so blessed to meet him and kind of thinking about the way that you saw him interacting with you from the physics side, anything that you'd want to share with us to build on that a little bit?
So one of the things that amazes me about him is that he has no musical training. That's the first thing that's interesting. He went to art school. He studied art, visual arts, and he wanted to paint with sound. Now, can you imagine some person saying, "Can I join a rock band that's a world famous rock band so I can paint sound?" Yeah, really? But he did that. All right. One thing I would say about Brian that I find interesting is he said to me one day, he goes, "You know what, Stephon? So much of what we consider to be beauty in our culture is concocted." I was like, "What do you mean?" He goes, "I've deliberately done things over the years that was deliberately ugly or what have you, and I manipulated culture to make it think that was beautiful." And this is serious business, but this is a person that actually did do that, right? Music for airports. Let's not get into what they can do there. Right. So again, he's either a madman or a genius, or a little of both. But he's a very generous person, and I look back and like, why was he hanging out with an idiot like me? He makes me realize that it's important to, no matter how big and how famous you get, right? Spending that time with people, it doesn't matter, it really matters. Because I got to write a nice essay about him. And for Wired magazine, you should check it out. It's called Eno, the Sound Cosmologist. Yes.
Yes, sir. I have my younger brother here. He's 14. He's really into physics. Obviously, he's a middle schooler. So, what's your best advice for him as being so young and wanting to be in the physics field?
I think it's important. First of all, we live in a very interesting time where a lot of information can just be accessed through the internet. So in other words, I think, just play Oracle. Any question that comes to mind, just Google it. In fact, I did the following thing. There's some nights I get, before I go to sleep, I get so bored. I start playing this game myself. So I pick a random word and another random word, and I put them together and I Google it and see what comes up. And then I read about it or watch a video about it. You'll be amazed the kind of dreams that it ensues later on. Actually, I want to do something interesting. I promise to play a little bit more for you. And I want to actually, this is mainly for the music students in the audience, but remember I told you about these waves and the Fourier series and all this stuff. And I told you that one thing that you should understand about waves, right, is to make a wave, you need to impart energy into the wave. And if you want to create a wave that's really rapid, I don't want to break my horn, you have to put a lot more energy into making a wave that does this. Right? I'm actually making a wave right now. It's just a wave in the position of the horn. But if I want to do this, I take a lot more energy. And one of the fundamental principles of nature is that Mother Nature likes to always minimize energy. Doesn't want to, anything that happens in nature, it's basically a way of being very efficient with the usage of energy. That's why if I fall off of the top of this thing, I'm not going to be like zooming around, zipping around and falling. I'm going to fall straight down, right? That's minimizing the amount of energy it takes to get from point A to point B. Okay? When the moon goes around the Earth, it's minimizing the energy. It's staying in a particular orbit for the velocity it's going. So that's what nature likes. Let's apply this principle to sound. So I told you that if I play a C, and I go up in half, that wave, right, is half the amount of the other wave. And so that's why you might want to think that the most consonant note, the most agreeable note is the octave, because they sound very similar to each other. So the next most consonant wave is the one by a third. So one question you can ask is, why is the perfect fifth? So imagine I lived in a universe where the universe only admitted the energetically most favorable notes. Let's take those notes. And what I'm going to do is take those 5 notes and I'm going to start from the lowest of those and go up in a scale. I want us to play the exercise, and let's close our eyes, and I just want you to hear it. Can we do that? Let's begin. Know that song? Okay. How about this song? That's a song also, based on the same scale. How about what? That's a pentatonic scale. That scale is based on physics. And it's the most common scale known to every culture. Thank you.
On behalf of Dean Wells and myself, we'd like to give you just a little.
$500,000 and
Congratulations. Thank you so much.